In this problem, we have a sled that is sliding down a snow-covered inclined surface. There's kinetic friction between the sled and the snow, and the sled is moving at constant velocity. And we'd like to calculate the incline angle such that the sled can slide down at constant velocity. So the mass m is given, mu sub k, coefficient of kinetic friction is given, and we're looking for the incline angle. So first thing first, let's draw a free body diagram, and then we're going to apply Newton's first law. Why is that? Because the object is moving at constant velocity, so acceleration is zero, both along the direction of the incline and in the direction perpendicular to the inclined surface. So in both directions, we have acceleration equals zero, net force equals zero. We are going to apply Newton's first law. So first, let's draw a free body diagram. Here's my XY coordinate frame for the free body diagram. I have tilted my coordinate frame such that the x-axis follows the incline angle. So the angle between the x-axis and the horizontal is going to be theta, and the y-axis remains perpendicular to the x-axis. So both of the coordinate axes are tilted. Why do we do that? Because the object is moving down the incline. Even though there's no acceleration, it's just convenient to tilt the tilt the coordinate frame like this. If there was acceleration, then really I strongly recommend you draw your free body diagram such that the one of the coordinate frame axes follows the direction of the acceleration. In this case, there is no acceleration, but we still tilt the x-axis because you will see that with this, we will only have one force for which we will have to calculate components using cosine or sine, but the other two forces will be either purely in the x direction or the y direction. So what are the forces acting on the sled? There's gravitational force pulling straight down. There's normal force from the surface perpendicular to the surface, and there's friction pointing in the direction opposite the direction of motion, which will be up the incline. So let's go ahead and draw these forces. Here I have all the forces shown on the free body diagram. Remember, the subscript refers to the type of the force. So I have gravitational force F sub g pointing down on the sled by the earth. The superscripts represent the object and the agent. And the angle, incline angle theta, is also the same as the angle between the gravitational force and the negative y-axis. And then we have the normal force applied on the sled by the inclined surface. It's normal force, so it's perpendicular to the surface, so it's perpendicular to the x-axis and it's on the y-axis, positive y direction. And last, we have the kinetic friction force F sub kf on the sled by the incline again, this time opposite the direction of motion, so it's parallel to the x-axis but pointing in the negative x direction. Next, let's apply Newton's first law in the x direction. Now, which forces will be in my force equation for that one? Kinetic friction force will be included because it's on the x-axis. Normal force will not be included because it's on the y-axis, so it doesn't have any x component. And the gravitational force will be included in my force equation for the x direction, but we will include its x component. So I am representing the x component of F sub g using this green line. It's a line perpendicular starting from the tip of the vector F sub g that is projected onto the y-axis. Also, it's parallel to the x-axis, right? So this is the x component of F sub g, and it's opposite the angle theta, so it's going to be sine theta. It's going to be F sub g sine theta. That is the x component of my gravitational force vector. We start with stating Newton's first law in the x direction. So that's net force in the x direction equals 0. And in the next step, we are going to expand the left-hand side of our equation based on our free body diagram. Again, we have F sub g that will go into this equation, and FKF, kinetic friction, that will go into this equation. F sub g has component x component equal to Fg sine theta, and it's positive. And then we have the kinetic friction force in the negative x direction. Because kinetic friction force is purely in the along the x-axis, we're not doing sine or cosine, we're just putting minus FKF. And this is basically it. We set this equal to 0. Now, let's remember F sub g, well, it's not a given variable, right? But we have a formula for F sub g. It's equal to mass times gravitational acceleration for the sled. So I'm going to substitute mg for F sub g in the next line. Also, kinetic friction force, again, it's not a given variable, but we know that there's a formula for it. Kinetic friction force is equal to mu sub k, a coefficient of kinetic friction, which is a given variable, times the normal force F sub n. So in the next step, I am going to substitute the defining formulas for these two forces. And here's what we get in the next step. Now, what is it that we're looking for? We're looking for theta, right? Theta is here. That's my unknown. Let's take a look at all the other, let me actually highlight it. All the other variables. Now, we have an equation that has theta in it. I'm going to isolate theta, and that'll be my final answer. But first, let me double check. Are all the other variables given variables in the problem? Because our final answer should be in terms of the given variables. So m, the mass of the sled, is given. That's in the picture, so that's good. G is a physical constant, so you can always have G in your final answer. It doesn't have to be given in the problem. Mu sub k, that's also given. Now F normal, this is not a given variable, so we're not done yet. That means we have another unknown here, right? So when you have two unknowns, you need another equation. And remember, we haven't applied Newton's first law in the y direction yet. So let's go ahead and do that. And if you think about it, look at the free body diagram. F normal is a force that's on the y-axis. So then when we apply Newton's first law in the y direction, then this will give us another equation that has F normal in it. So we can isolate it and combine with this equation to eliminate F normal. So that's the plan. Let's go ahead and set up our force equation in the y direction. Again, let's start by stating Newton's first law in the y direction. Net force in the y direction equals 0. That's my starting point. Also, on the free body diagram, I highlighted the y component of F sub g. That's the purple segment. And you can see that it's adjacent to the angle theta. So that's going to be cosine theta. It's also pointing in the negative y direction. So the y component of Fg is negative Fg cosine theta. Does kinetic friction go into this equation? It doesn't, because kinetic friction doesn't have a y component. On the other hand, F normal will be included in this equation because it has a y component. It's actually purely in the y direction, and it points in the positive y direction. So that's going to be plus F normal minus Fg cosine theta equals 0. So here it is. Here's my force equation in the y direction. In the next step, I'm going to do two things. I'm going to substitute mg for F sub g. I'm going to also rearrange my equation to isolate F normal. And here's what I get when I do that. F normal equals mg cosine theta. Now, is this a useful result that I should memorize? Absolutely not. Never memorize it. F normal is not necessarily always equal to mg cosine theta. It happens to be equal to mg cosine theta in this particular problem, but it's not something we should memorize. We should always draw our free body diagram, apply Newton's laws, and then come up with the force equations. Now, what do we do next? Next, we are going to actually use this result, take this result right here. Sorry, I I want to highlight this. F normal is mg cosine theta, right? Take this and substitute it right here. Right here. And rewrite the first equation. So that way we will combine the two equations to eliminate F normal. And here's what we get when we do the substitution for F normal. And what do we see here? We have some variables that cancel, right? There's m in each term, so m's cancel. There's also g in each term, so I can divide both terms by g. G's also cancel. Now let's rearrange our equation and isolate theta. Maybe I'll do that in 2 steps actually. Here I have rearranged my equation after canceling m and g. I get sine theta divided by cosine theta equals mu sub k. Now sine theta divided by cosine theta, that's tangent theta, right? So tangent theta is equal to mu sub k. But we're really looking for theta. We want to isolate theta, right? Now we need to do the inverse function of tangent on both sides of the equation. What is that inverse function? It's just inverse tan. So then theta is going to be equal to inverse tan of mu sub k. And here's our final answer. Now inverse tan is also called arctangent, so both are the same thing. Theta equals inverse tan of mu sub k, or arctangent of mu sub k. Now, does this make sense? Dimensionally, is this consistent? Let's take a look at that. Now, what is mu sub k? Mu sub k is just a coefficient. It's a dimensionless number. It's just a number. It doesn't have a physical dimension. It doesn't have a unit. And tangent of an angle also is just a number. It's a unitless number. So it makes sense that tangent theta ends up being equal to some number. It makes sense that mass and g, all those cancel, such that as a result we just have a dimensionless number as the tangent of our angle. So dimensionally this is consistent.